So it's 10 sharp. I'm going to wait 2 or 3 minutes for some stragglers, but I'm going to start talking anyway. Right? Just got a question which reminded me that last week in the intro, I was planning to say something, but I didn't. Namely, that, well, I do expect everybody to be able to read, right? I mean, I think I literally said this, that you should have learned hopefully in elementary school or soon after. But none of you have much experience with reading scientific papers. And what you probably will do when you start reading a scientific paper is use your general reading skills. You start from A, read it all the way till the end. If you don't understand something, you gnaw on it, you read it again and again and again and again. Yeah, you could do that. That is one possibility. It is not, in my personal belief, the best way to read scientific literature. Because scientific literature is written by somebody who did not necessarily get their PhD for their writing skills. They got their PhD for doing good science and being able to communicate this well enough to an audience of peers that they're like, yeah, this person is not stupid. But they can do science, right? That is the general idea, which means that most scientific literature is pretty badly written. And it's sort of the type of text that is not really meant to be read. It should be understandable enough, but it's not the best way to communicate. Most people, myself included, only start to understand what we're talking about while we're writing the paper. That sounds a bit weird because typically we write the paper after, let's say, half a year of study of the topic, right? So we know something about it. But to quote Richard Feynman, I mean, you don't truly understand something if you can't explain it simply. And in most cases, when the moment you write a paper, you don't understand it well enough. You can't explain it simply. You understand it through the line of thoughts that you've been following, right? Which makes sense or made sense for you at that moment, but may not be the best way for a general audience, right? So there are, of course, exceptions. There are papers that are beautifully written, and you can read from A to C and you get the brilliance immediately, right? But those are relatively rare. So one of my didactic goals for this course is not only to, well, help you train your skills in critical thought, but also your skills in reading academic literature, scientific literature. In that sense, it's a little bit like a seminar, this course. Now, I've been thinking about this for quite a while. I mean, I've been teaching this course for a long time, and before that I've also been thinking, how can I teach this? And, well, effectively my conclusion was I can't. I mean, you just need to do it. And then, well, if I force you to read quite a lot, you will need to develop these skills because it's going to be sink or swim, right? Which means, like you were saying, that how to deal with the optional or the required literature for the lectures, because, well, you're admitted to not being the quickest reader yet, right? Yeah, neither was I when I was in your shoes. And how did I learn it? By doing. And that is out of all the different ways of I've been looking into how you can read, how you can learn how to read. It's just by doing. Now, my advice is to take a scientific paper and do not read it from A to Z. Do not try to understand every single word. Every time you get stuck, just power on. Just power on. We're all smart. Otherwise, we would not be at the university. Otherwise, you would not have gotten a bachelor's degree, or you would not be a bachelor student, right? You would not even been enrolled. So you should not immediately claim, okay, I'm God's gift to science, right? I mean, that's, or God's gift for whatever, right? I mean, let's keep the egos down a little bit. But just power on and try to get the gist of it. The most important parts are generally the first part, the abstract and introduction, and the final part, the conclusion. Those do not include the core mathematical ideas. You will not be able to reconstruct the paper just from these tails, right, or the head and the tail. However, if these papers are halfway well written, they will include the general ideas that will help you to understand what on earth are they trying to do in the middle. So first, read start and end, right? Try to understand the gist of it. Then power through, well, the details. That could be the theory, the mathematical details, right? And some of you will be more mathematically oriented. Like, okay, words, right? Give me math. Much easier to understand. Good for you. Focus on the math, right? That's why it's there. There will be some of you who are like, well, math, right? Give me words. Rather give me the... Great. That's why the words are there. This is also why a carefully crafted scientific paper includes both, right? It explains the ideas in words and it defines them in math. and often does this multiple times because, well, readers are humans and humans are kind of stupid, so we need the power of repetition, right? This also means that really reading a paper from A to Z is going to take you, just by definition, way too much time because the same idea will be presented multiple times. So pick and choose what works for you. And the moment that you have the general gist, then you can, if you feel the need for it, you can drill down a little bit. Like, hey, wait a second. They said they this, and they write, I don't understand this fully. Let's read this part a bit more carefully. So effectively, it's sort of like a upside down pyramid, right? First get the general idea, broad strokes, and then drill deep wherever you feel it's necessary. And this is really, I mean, you need to develop some instinct, some gut feeling. But it also goes hand in hand with your own interests, right? If this is a paper on a topic that really doesn't do it for you, okay, just make sure you understand it well enough. But if this is something that really resonates with you and you really want to know, like, how are they doing it? Why this doesn't make sense with regard to what I've been taught in another course? Okay, then focus and spend some brain energy on those parts that, well, make your heart beat faster or slower. Good. I hope that answered the question, and I hope that also partially, let's say, resolves some doubts you may have, like, what on earth is he thinking with this setup? Okay, it's 6 past, so this intro took a bit longer than I planned, but I'm going to say now, welcome, everyone. Second lecture of TADA, and today we're going to be talking about patterns. Now, we are humans, and humans are very good at seeing patterns everywhere, even if they're not, right? But what is now truly a pattern? What do I mean with a pattern? And why haven't you heard about patterns and the type of patterns I'm going to be discussing today in any other machine learning lecture? And that's actually a question I can't truly answer, but we're going to give it a go anyway. The other way to phrase today's topic is, how can we discover from data that is, well, sufficiently large, sufficiently complex, inherently interpretable models that are at the same time also useful? Because if we learn, let's say, a linear regressor or a linear classifier, reasonably interpretable, but it may not be useful, right? It has very limited uses, and vice versa. Some models are super useful, but we have no idea what they're doing. So how can we balance this? Now, first things first, what is a pattern? A pattern is a form of recurring structure, today at least, in this lecture. So if the data looks like this gray blotch over here, this is of course very abstract. What is the pattern? This part we see a lot in this image, right? I mean, I'm not going to be talking about image data in this lecture, right? It's just really just to illustrate, because otherwise it gets too abstract. Same thing here. We have this, I'm not sure if this is wallpaper or a shirt, but it does give me a migraine. However, the pattern is this little figure over here, right? I mean, that you can find this many, many times there. There are also other patterns in here. In this one, not so much. In this image over here, what is the pattern? Clouds and raindrops. And again, you could say, well, actually, well, no, my pattern, I think there's clouds, and the other pattern is, I think there's 3 sizes of raindrops at the very least. There's a small raindrop and there's a large. Those are the patterns. And, well, I would agree, right? I mean, there is multiple patterns in these images. What we're interested in today, how can we, given a database that doesn't look like an image, how can we extract those patterns? And if you now quickly think about it, that is not something that your standard machine learning toolbox helps you to solve. Because is this a classification task? No. No, the classification task would be, given a pattern and a data set, is the pattern in the data set, right? This is called pattern recognition, another name for computer vision, amongst others. That's not really what we want to do here. Is the regression? No. So how much of a pattern? This is again it's unsupervised. Given data, we want to extract something. You don't know, most likely, many unsupervised machine learning or data mining techniques. Because somehow in every lecture they say, like, oh, this is really important, right? We have supervised and unsupervised, they're equally important. Let's spend the entire lecture on supervised machine learning. I'm also guilty. If you take an EML, then you know that, but you first need to lay some basics, some foundations before you can go to the more advanced stuff. One of the few unsupervised machine learning techniques that you may know is clustering. Well, is this clustering? No, not really, right? I mean, that's so if this is a database, then these would be the records, these would be the features somehow, but I mean, all the records looked at, no, it's not clustering either. So the task of, given a database, how can we extract all things that happen frequently, that happen multiple times. And ideally, that happens so often that we say like, hey, yeah, this is worth knowing, right? If we want to know about this data, what are the building blocks of this data? Those are patterns. How can we extract those? Now, to do a slightly less abstract example. Here we have some data from toy data, obviously, from a supermarket. These are the customers of my supermarket, and I've been keeping track of, at the cash register, what they've been buying. And I do this very simply. It's basically if somebody buys a product from a certain category, in the corresponding column in my database, I set a 1, right? And if they don't buy from a certain category, it's a 0. And I can do this per category. I can do this per specific make and brand of a product, right? I can do this at any granularity. What we see here is that this person, let's call him Bob, Bob bought diapers, he bought beer, and he bought crisps. Well, okay, that could happen, right? I mean, then this is then, I guess, Charlie, I don't know. And he bought apples, and again, diapers. I mean, lots of people with kids, apparently, or other things that we don't want to think about. And again, beer, and so on and so forth, right? I mean, some people also bought pasta sauce or dipping sauce. Doesn't really matter what it is, right? You get the general gist. Now, if we have such a database, we can count how often we see a pattern, right? In the previous example, that was a bit abstract. How often do you see a cloud? Okay, fine. How often do you find this grating thing? That's more difficult. Here we can ask, how often was diapers sold? And we call this, in database terms originally, the support. So this diapers and beer, by the way. Okay, diapers, beer, simply counting how often do we see them combined. Well, effectively, how you can think about this, for those of you who love databases, please all raise your hand. Oh, you love that? Okay, so there's people who love databases. Very good, very good. I mean, I have a love-hate relationship with databases. Part of my work is based on insights from databases, but I hated the course. I really, truly hated it. But effectively, you could see a pattern as a selection query, like a very simple SQL selection query. Select all records where we see diapers and beer in this particular case. That gives you a certain set of records, right? And then you can just do a count over this. So it's a count select SQL query. And what we're now interested in from that perspective, find all such queries that for which the count, right, for which the support is at least so and so high. Because some unique combination of products, right, that you may have bought or you may have bought may be interesting but not so likely, right? But let's say if beer and diapers get sold many times in our supermarket, well, that is worth knowing, because then we can put an advertisement on the one in the hopes that people buy the other, or vice versa, or maybe we put them a bit closer to each other in the shop, because then more people are more likely to grab them, or vice versa, we can put them further away, such that people need to maneuver all the way through the shop, right? That all depends on what is the, let's say, the semantic meaning of this pattern, right? But we can do stuff with this type of insight. So we can optimize our business. Are we stuck with supermarket data? No, no. First of all, supermarket data is just like a motivating example. I mean, I couldn't care less about supermarket data. However, if these are still people, and the columns are now certain genes or mutations of genes, then all of a sudden, the task becomes much more interesting from a biomedical, from a health perspective. Which combinations of mutations of genetic variants or epigenetic variants, or I mean, you can, well, unleash an entire dictionary that you may or may not be aware of. Which combinations are particularly prevalent in, for example, among a set of patients that suffer from a certain disease? All of a sudden, we can find those genetic drivers or insights into the genetic drivers of diseases. That's pretty cool. I can go on and on with tons of examples, right? In material science, in general physics, in... Hi, Anton. Oh, you have a question? Okay, I thought you just wanted to wave.
You mentioned like this biomedical data thing,
Yeah.
but this person with this set of genes has like this certain illness or not.
Yeah.
Isn't this essentially pattern recognition?
No,
reverse?
because what is the pattern?
Like, that's true, I agree. However, if we have like an illness or something, we can like use this as like the output, right?
Also, suppose that all these people suffer from celiac disease, gluten intolerance.
Like
all of them, yes, all of them, yes.
Yeah, then it doesn't.
Or they all suffer from, I don't know, If I say breast cancer, then well, some of them had a haircut, maybe, I don't know. But anyway, some form of cancer, right? I mean, that I said breast cancer because there's different genetic variants that I know of breast cancer. There's many cancers where there's different variants, and we don't know what the variants are. We just know that all these people suffer from, I don't know, throat cancer. What are the patterns? Basically, what are the patterns is the one question, but what are the class labels? What are the subtypes? Can we find that? And now, hopefully you see that, hey, now things get interesting, because if we don't know these class labels, what on earth would you do? You could cluster and whatnot, right? But then you would still need explainability. It's on what do you cluster? Clustering requires a distance metric. How do you define this, right? I mean, clustering is a bit of a weird construct, but effectively we say that, hey, we know this is how records are similar, and now give me the grouping that adheres to this similarity, which is, we don't know what is similar. Right? I mean, this is sort of like putting the horse behind the carriage. What we want to find out, what makes certain people more or less similar, and those are the patterns. So effectively, what we can be doing here is developing a similarity metric that makes a lot of sense for this particular type of data, such that we can find what are the subtypes of cancer. Or in this example, what are the groups, let's say the subpopulations of our customer base? Because there could be young parents, there could be students, there could be professors, whatnot, right? All of whom have slightly different buying patterns. How do we find this out? If we don't have the labels, and okay, this is a student, and typically your supermarket doesn't know what you, and that also privacy laws sort of bite there. But how? So this is unsupervised learning, what we're doing. So clustering would require a similarity metric. Then if you know what the similarity is between each of these groups, sure, but then you kind of already know the answer, right? Then you don't need to do the clustering to begin with. Unless you say like, well, I'm going to try this and then see what it gives me and see if I like it. But clustering is a very weird beast. Yes?
Whenever, or do we imply with that they have some sort of positive impact, or like a combination searching for, do we just about any?
So far, right now, in this part of the lecture, any. It's really just associations that we're finding. It's really people who buy diapers, right? Reasonably often also buy beer, and or vice versa, right? This is not conditional, right? It's really this, I often see this combination. It's not that this combination of genes causes the disease, but people who have this disease, right? Suppose that all of these have one disease, happen to have this combination of mutations remarkably often. And causation, correlation is not causation, right? But it can give you a fingernail behind what might be the driving cause. Later in the lecture series, we will arrive at causality, and then we'll see whether or not we can interpret these bastards as causal and under which assumptions and so on. But right now, no. It's just people buy beer and diapers more often than perhaps you might have suspected in my supermarket. Are we limited to just binary data? No, no. If we have just continuous value data, we can define a conjunctive formula, like here. This is for the Iris database, the Fisher database. Petal length smaller or equal than 2, petal width smaller or equal than 1/2. Well, it's an SQL selection query, right? It selects a number of data points, and we can now start to reason what are now those queries that select remarkably many records. That's effectively what we're after, right? Also note that what we're doing here, so if we have petal length smaller or equal than 2, in a way, behind the scenes, even though this is really on continuous value data, we turned these columns into binary columns. Because we have now a magical column, is the petal length lower or equal than 2, then it's a 1, and otherwise it's a 0. And the same thing for the petal width, right? So behind the scenes, it's binary data. Binary data always seems a bit stupid, but it is very powerful. Molecules. Who doesn't like molecules, right? I had a very nice cup of molecules called coffee this morning, and otherwise I would not be a functioning adult. How do, or for a large part, that's technologies differ and change, but one of the standard techniques for discovering new drugs for a particular disease is that you take a cell that has a certain disease, right? Actually, no, you take a cell, you clone it. many, many, many times, right? Millions of times. You make sure they're all equally sick of the same disease, right? And what we then do, we have a so-called screen of, let's say, basic molecules, basic ingredients of which potential drugs could be based upon. And for each of these cells, they get one of these candidate, well, these drug components, let's call it that, right? And then we sit and we wait a little bit, and then we see, okay, for which of these molecules, well, for which is the disease dead, right? Is the disease gone? And well, then you could say, okay, let's just use one of those. Well, typically it also kills the cell, and if not the cell, it would kill the host, right? Because many of these things are highly toxic, and we're not done yet, right? However, what we can do, if we now know that, for example, these three molecules, they would all kill you, but they also kill the disease. Now, we can ask the question, what is common between them? So which, let's say, molecule ingredients do we see very often in molecules, right, that are active against, well, the disease or whatever, I mean, we're interested in, right? The effect that we want to. In this particular case, is this benzene ring with a nitrogen and an oxygen. So this little tail here, that is common between them. Well, I'm not a chemist, I'm not a pharmacologist, but this is an ingredient that we can give to an expert. And it's like, wait a second. This thing, we know it has an activity like such and so, and we know that if we don't have, let's say, some fluoride tail here, then it's toxic as hell. But if we add this, it's going to be fine. Or let's see what we can do to this bastard to make it less toxic, right? But at least you've got now inside a starting point from which you can start to explore, right? Remember this fourth paradigm I was talking about last week, right? I mean, giving a candidate hypothesis from which you as the human can then reason further, and then we can see, okay, well, if we now have a set of candidate molecules, we can again see which of those work or don't work, and so on and so forth, right? Good luck doing this with standard machine learning tools. Yes?
So is attention something like this? Like when we use attention, it gives us some pattern within the data set, and then we apply, let's say, linear net. So isn't it something like having a pattern and then we...
I need to use my favorite German word, jein. You know jein? No. So you know the German word for yes? What is the German word for yes? What is the German word for no? And if you combine them? Good. I don't know. I don't know. I'm not a native speaker. We can discuss this later. It's definitely a no. If I want to answer this question in terms of, does attention explicitly point at patterns like this? The answer is no, or at least nobody has figured out how on earth from transformer from attention mechanism we can extract this, right? What we can do is, for many records, figure out where does it attend to most, right? And if we binarize that, and then we apply a technique like this, then perhaps we can sort of but yeah, that is not really the same thing. At the same time, I do strongly believe there is also a part of a yes, because in order to classify and predict very well, a neural network or any machine learning model will need to understand what are the patterns of the data. And understand is a very strong overstatement here, right? It somehow needs to be embedded in this network. Now, our goal right now, here today, is how can we extract it? And we can try to extract it from a neural network, but let's first try to extract it from some data, and perhaps later in the course we get closer to what you were alluding to. No. Because we can develop methods that work for binary data in general, and then whatever binary data set you give it, there you are. Which in a way is superior to let's say, a pre-trained neural network, because that will be very dependent on which data you have been training it on, and whether that data exhibited a type of patterns that the data you're looking at will. So if you train on everything possible, then it will maybe do it, right? But now we can make things much more explicit. Good. So traditional pattern mining is a topic that, well, exists already since 30 years. I mean, this has been anything but hot, right? I mean, I still think it's cool, pattern mining, but not traditional pattern mining. The standard definition as posited by Srikant, Agarwal, Manila, and Toivonen back in 1994, two independent discoveries, some of the most cited papers in CS. We have a database, transaction database, we call this binary database, where transactions are basically the shopping carts, right? I mean, so I will use binary data and transaction data exchangeably. And what we're then basically going to do is we'll develop algorithms that mine all frequent patterns that have a frequency or a support, people use these words interchangeably, of at least sigma. At least some minimum support value. In my terminology, I typically use support for the absolute number, for really the count, how often do we see beer and diapers, and frequency for the relative number. But in the literature, people exchange this all the time, and well, my slides might or might not do this too. So the way how we do this, these algorithms, they're cute, they're nice. I could explain them. I explained them in one of my intro lectures for the perspectives of computer science. I'm not going to do this today because I want to catch up a little bit beyond 1994. But there are algorithms that, even though this output, actually wait, let me see. Suppose I run a supermarket and I have 10,000 products for sale, right? Not even a big supermarket, more like a local supermarket. Suppose that I now collected data over a long, long time, right? I mean, so I have enough data. How many patterns can there possibly live in my data?
Somewhere around the order of 2,000.
Somewhat in the order of?
Yeah. So I don't know if it's exact because it's probably a pairwise instead of just like 1.
So it is 2 to the power 10,000 minus 1 because we ignore the empty set. Right? That one I can give you for free. That is a very large number, right? This is where people say that only mathematicians consider this finite. But of course, my customer base is not going to buy every combination of products, right? I mean, at a certain support threshold, right? I mean, that would really be sort of a random type of customer, and I expect that there is some buying pattern, so otherwise I would not be looking into this data. I expect my data to be reasonably sparse, in fact, because I don't know how many products you typically buy if you go to the supermarket, right? But if you buy up to 10,000 products, then I don't know. I would want to know how you finance this. So typically these matrices are relatively sparse, and automatically this means that the number of patterns, item sets we also call them for binary data, the number of these item sets is actually, well, a bit more bounded, but it's still exponential in the number of items overall, the number of columns overall. And the problem is that if you now set such a threshold, you're going to get very, very many of those. I'm going to give you an example. This is for a database on different chemical properties of wines, right? There is white wines, there's red wines, and there's rosé. And this is the minimum support threshold, right? So basically, how often does a combination of properties need to occur in this data before we report a pattern, right? And this line here, as you can see, it goes through the roof, right? This is to indicate that it becomes very big. This is a database of a whopping 178 rows, right? So 178 rows, you can still kind of plot and just stare through the hairs of your eyes, right? And maybe see something, right? I mean, good luck with that. But now if we do this frequent pattern mining thing, I've just been telling you like how fantastic this is in theory, and we set the threshold at around 100, we don't get anything. Yeah, okay, duh, right? Let's say that roughly half of the data, we don't get anything. Okay, let's go to the third of the data. No, well, still almost nothing, right? And then all of a sudden it explodes. At the top of my head, it goes to 2.8 million. Which, well, we went from the problem of that, hey, this data is too difficult to see any patterns in, to, oh my God, I have so many patterns, I don't even know what to do with it, right? There's more patterns than you can shake a stick at. Okay, not so great. This is why pattern mining, the traditional notion, was doomed from the beginning. We call this phenomenon, this explosion, the pattern explosion. So for high support threshold, high frequency thresholds, you get very few, but typically very well-known patterns. So in the supermarket case, you're going to get the bread and butter patterns, as I call them, right? I mean, that's just the stuff that, I don't know, as if you're running a supermarket, you should know these patterns, otherwise you should not be running a supermarket. But the moment you set these thresholds relatively low, then you have this giant explosion. Well, we already know this is an exponential output space problem, right? That's what we just established. But why do we see this sudden explosion? Does anybody have an intuition? Where does this come from? You have an idea, Anton?
Going to share my fourth slide.
Yeah, please.
So essentially, if we think like in the maximum, then essentially like one record or like one record is like everything, right? And
Yeah.
no one buys everything, right?
No.
And if we reduce the number of items in this record, well, at some point people only buy like two different things or something, but there are a lot of people who buy like two different things.
Mm-hmm.
That's why essentially from nothing, like kind of nothing because no one does that much, everyone does it. So that's why it explodes.
Yeah, yeah. So
And
okay.
it's also not only the number of people who do it, but also within one person,
Mhm.
you can also like associate like different items with each other, right? So
Okay. So the
as soon as you have like three items, you can like have one.
exactly. That is the first one is where we get the potential for many patterns from, but the second one is where really the explosion comes from. Just imagine, right, that we live in a neighborhood where people like to make, I don't know, pasta, right? If you don't like pasta, you can exchange the example with curry or whatever your favorite dish is. So if I make a pasta, what do? I need I need to buy pasta, right? I mean, that's, what else do I need? I need olive oil, right? Because that's, I need good tomatoes, these Mazzarano tomatoes, right? I mean, either canned or not, I don't really care, right? I mean, I need some tomato paste because you need to make it extra tomatoey, the sauce, right? I mean, you need some minced meat, be it vegan, vegetarian or whatnot, right? I mean, your choice. Let's see, we have a mozzarella cheese I typically add. I mean, that's we have Parmesan, basil, right? Okay, we have 8 products, right? 8 products, right? I typically make a more extensive pasta, but then we need half the lecture. We have 8 products. Suppose that I'm not the only one who buys this, right? Or actually suppose that I'm the only one who buys it, but I do this very frequently, right? I mean, so I buy this frequently enough, right? I mean, I make this every day, and I speak it with the Italian accent because I eat so much, but I know. It becomes frequent, this pattern. What happens in this data is that all of a sudden, all subsets of these 8 are also frequent. Automatically, just by definition, right? Even if I now bought like all these 8 ingredients every time, then it also means that, well, the set of ingredients, but minus the pasta, or minus the tomatoes, or minus the basil, and so on and so forth, right? And any subset thereof. That creates how many item sets already? 2 to the power 2 to the power 8. How many is this? 256 minus empty set 255. Okay, that was just one real pattern, and this explodes already, right? But suppose that we have, in addition, another pattern that basically everybody buys bread and butter, right? Almost everybody. That also means that my pasta pattern, yeah, so the times that I buy pasta, those times I also buy bread and butter because I'm a normal human being and I buy bread and butter in this universe. That means we have 10 items already. 2 to the power 10 is, hey, now we're already above 1,000 patterns that just get generated because there is one bread and butter pattern, really small, and one real pattern that is not even that large. So this combinatorial explosion hits you really in the face there. Now, there have been attempts to count them differently. Let's not report every subset. If there is a superset that has the same frequency, if we do this, if we do that, to quote the great philosopher Donald J. Trump, sounds good, doesn't work. Or it doesn't work, I think. Because of this explosion, I'll be with you in a second, because of this explosion, many patterns will be also very redundant. There will be variations of the same theme, right? So just as a small aside, suppose that I am not as consistent in always buying these 8 products because sometimes I have some leftover basil, some leftover pasta, whatnot, right? I mean, that's, and you make your variants of pasta and maybe you don't like adding this or that, right? So this means that for every subset, there's also a slightly different frequency, right? And it's very difficult to set like, okay, which one is it now, right? I mean, is your pasta the definite pasta? Is your pasta the definite pasta? Or is it more a general set of products? So it's very difficult to pin this down, which creates this redundancy. If we just count or if we evaluate every pattern individually, does it occur frequently enough to be reported? Yes, we report it. Just by doing everything purely locally, you invite a very big problem.
So something is like at the support of like maybe 30 or something, where we find something but not too much, right?
Yeah.
Couldn't we just do binary search on the support? Then I know like
Mhm.
it's like exponential thing, but
Yeah.
for binary then we have like linear time or something, which is like acceptable.
Sure. So, but this makes sense if we want to constrain the number of patterns that are reported, right? So, my favorite question is what could possibly go wrong if we would follow this? If we said, okay, 30 is the magic number, right? Or actually 42. 42 is a much better number. 42. But what would this mean if we set the support threshold to 42? Because then we get a reasonable number, right? And then, yeah, I'm just trying to see if somebody else may not. Do you have an idea, sir? Yes. Yeah. If we set the threshold to 42.
In this particular data set.
Yeah.
You were arbitrarily constraining your selection.
Yep.
This is not potentially not justifiable.
Yep. Yeah. So if we now reason, so what are the things we will not be finding if we set the threshold to 42? Yeah. Yeah. Exactly. So would you say if I set the by binary search or whatever technique, right? I mean, we set the threshold at 42. I mean, is 41, are those patterns then all of a sudden super uninteresting? We don't know. There might actually be patterns with a support of 10 that are very interesting. I mean, mine, or 18, let's say 18. 18 is still 10% of your data here, right? If 10% of my customer base buys a certain combination of products, I can still make some money out of this. It's still worth knowing. If it's just me who buys some freakish combination of things, right? I mean, even that may be of interest if I do this often enough, right? I mean, that's because, well, let's give me a customer card or whatnot, right? It's just, so a hard frequency threshold is very tricky. It's very tricky, right? So, yes?
Have a very large amount of food
Mm-hmm.
categorized as like veggies or bakery items, so we can have like less patterns as compared to having like 1,000 goods.
We could, in theory, do this. But then the question becomes from, we have a second problem in a way, because the problem that Anton sort of touched upon is like, how do we choose the support threshold? And frankly, the answer is God knows. And in your solution, I mean, it would, of course, reduce the search space massively and the output space, right? But if we said, okay, let's put all the vegetables into veggies, right? Maybe there was a pattern, I don't know. Yeah, exactly. So something like this. Tomatoes, carrots, whatnot, right? I was actually thinking more of a mango, sweet potato curry or something like this. But okay, so all of a sudden it's just, well, veggies get sold often. So we lose the granularity of what is happening inside veggies. Or what is happening, for example, if we do go for the curry example, that, okay, well, mango and then cocoa milk. Right? Those coconut milk, I mean, those can be bought often together because these are ingredients for, let's say, a Thai curry or something like that, right? So the moment we coarsen this too much, then we lose this. So yes, it makes a lot of sense, but at the same time, we lose insight. Yeah.
Like we are getting very large amount of data set. We are just dealing with vegetables and inside patterns of the vegetables.
In theory, we could do.
Put pasta and tomatoes at one side of the store and the other vegetables and.
Why not? And like for an advertisement, right? If I specifically advertise, well, pasta, probably the sales for pasta sauce or tomatoes will go up, almost irrespective where in the store they are, unless I hide them, right? It's really like Easter and we just hide them like the eggs. That's something that we are not going to do. But for example, if we would just look at the vegetables, then we will not be able to find patterns like, for example, mango sticky rice. Right? That's basically because mangoes are in vegetables, rice are in whatever rice products are, right? And the coconut milk is in whatever. So we would really need to look at all these three categories at the same time at the right granularity, otherwise we can't find it. So it's a good idea, but sounds good, doesn't work, right? Good, yeah.
We're not able to find a pattern for those 8 ingredients because it's occurring so many times.
It's the opposite. It's more that we find too many patterns. We don't find the one pasta pattern to rule them all. We find 1,000 pasta patterns. And in a way, we would just like to have one. Which brings me to, well, actually, no, first this. I mean, this is why I chose the picture. A small change in the data, right? So you can imagine that if there is a big distribution in the sky from which we sample n samples, so one data set, right? And we do this twice. We have 2 data sets, right? We have exactly the same size, right? The distribution is the same, right? So let's say this week and next week, something like this, or today and tomorrow, right? There is no significant domain shift. Of course, the frequencies of how often people now actually buy pasta, I mean, yeah, this might be 10 here and 15 there, right? Now, depending on where you set our threshold, if that is at 12, then here we report it and there we don't. And because of this explosion, this means that either we do get 1,000 patterns extra, or many more, right? Or we don't. So the whole result set is also very unstable, which is not really something you want. You would like to have the situation where if you get data that is really the same distribution, that you also get the same result for some definition of similarity, right? Same does not have to be equal. So now we are at the start of my PhD, which is almost 20 years ago. So again, it's not a hot topic, right? I mean, that's pattern mining, but it's still very cool. And as you see, there's still a lot of work to be done. And we realized that we were asking the wrong question. And we being not us, but I mean people in the research community. People were asking for, given this database, I want all patterns that are so and so frequent. And that's, well, if you ask for all, then you're going to get all. But actually, we don't want all. We want a small set. I just want to have a pasta pattern. Whether this is the pasta pattern, right? That would require that there is such a thing, right? And that, but I rather have a pasta pattern that gives me some insight in the data, like, hey, people buy this combination of products, and that there is some variance of it. Who cares, right? If there are now significant variations of the pasta pattern, that I would like to know again. Suppose that now my supermarket is set in a neighborhood where there's a lot of students and a lot of professors, right? So professors buy the ingredients like I do, right? Because, well, they have money to spare, right? I mean, that's and there's also a lot of students. Well, students A don't have time to spare, or money to spare, and B, they don't have time because they need to study, right? I mean, that's so the student pasta pattern could be pasta and ketchup, right? Or perhaps a little bit more, but you know what I mean, right? I'm just going to go quite excessive. Let's say pasta and tomato sauce, right? I mean, that's very basic, which could be a sub-pattern in a way of the professor pattern. But if there are, well, if there's just one freakish professor who buys this in like once in a blue moon, I don't want to see it reported. But if there's a significant part of my buyers do buy this, I would like to get both. So we want to characterize the distribution. What is a small set of patterns that generalize the data very well? That's what we should be asking. So we should ask for a set of patterns, not for all patterns, but a set of patterns that each of the members of the set satisfy the constraints. So you could say that just out of definition, I insist that every pattern needs to occur at least 42 times, because otherwise, I don't know, right? I mean, this goes against my religion. And this set needs to be optimal with regard to some criterion. Okay, before we define this criterion, let's build some intuition. Let there be data. Here the data is that the whitish parts here, these are zeros. The grayish parts are the ones in the data, right? So, and the records are then again the people, and the columns are the products, right? I mean, that's what would a good between quotes, because we're building an intuition, what would be a good set of patterns for this data? Does anybody have an intuition? Anton?
So I kind of two things, like one is like the entire column where like the arrow is pointing at.
This one?
Yeah.
Yep.
And then you need next to it like the lower half of the people of like,
Yes.
and, like 3 or 4 things that belong together. Yes.
Yeah, exactly. So depending on how much we scale the number of records, right? I mean, so it kind of looks like this blue bar might be one person. This might be 1,000 people, right? I mean, it's still many fewer than the orange long bar, but if there's enough, right, if we scale it up, I would like to find. I would say that these are perhaps the 4 patterns that I would like to find in this data. If it's noise-free or whatnot, right? I mean, I'm just swiping all sorts of things here under the carpet. What I don't want to find is something like this, where basically every subpart of every pattern, right? And it's not every subpart, it's just mean all the parts that I felt drawing until I got bored, right? And this is what standard pattern mining does, but this is what we want. So how can we now go for this? So what is the optimal set? Well, the optimal set should somehow generalize the data, right? So we want to do induction. And if we want to do induction, we should use an inductive principle. Okay, who knows an inductive principle? Say that again?
I thought maybe not under that name.
Okay, that is possible. That is possible. So. Now, one thing that was our observation is that a pattern, in a way, describes a part of the data. That's quite literally what we see here, right? We can kind of color part of the data, right? The blue thing says something about that part of the data. The blue thing doesn't say anything about the rest of the data. It's really a local statement, right? Same thing about the orange thing, right? It says something about that part of the data, nothing about the rest, right? It describes data. What we can consider is that, hey, let's now find a set of patterns that together describe the data well. Okay, well, what does well mean, right? I mean, that we would need to formalize. And the good thing is that, well, we don't need to do this completely from scratch because there exists something called MDL. And MDL is the induction principle for descriptions. So MDL is a great choice. Who knows what MDL is? Wow, okay, this is, okay, I'm impressed, I'm impressed. Okay, then I'm going to bore the hell out of you. That's maybe not. Okay, good. So let's start with Kolmogorov complexity. Who knows Kolmogorov complexity? Almost the same set of people. So that's okay. That's I see a pattern here. Who knows what a Turing machine is? This is a serious question. Okay, good. So there's a few people that don't raise their hands. I mean, that so either you're shy or you don't know. I'm going to not explain what a Turing machine is from scratch, but a Turing machine is a theoretical construct, right? Developed by Alan Turing in, I think, 38, 39, in the 30s. I mean, that's based on other theories of Alonzo Church, whatnot. It's basically the most basic mechanism you can think about for computing. It's effectively the most simple computer you can think of. It has a long or infinite tape. It can read letters from this tape, and it can write letters on the tape. And then it reads things based on how it's programmed. And then, well, based on what it's read and how it's programmed, it starts to write things. It reads this again. So this is a construct on which you can, well, reason about what computers can do, right? On the computability of numbers is the paper at the top of my head. That's a Turing machine. So a Turing machine is basically, what you could say, a program for your favorite programming language. This is how you can think of it, right? And your favorite programming language, what I do assume, is that it's Turing complete. What does that mean? Well, that basically a Turing complete language can compute anything that is computable. That's roughly what it comes down to, right? So if you develop your own programming language and it can only do addition, okay, there's plenty of things you can't compute, it's not Turing complete. Your favorite programming language, if it's Python, C++, and so on and so forth, they're all Turing complete. Okay, now we can finally arrive at what Kolmogorov complexity is. So, say it again, esoteric? Most. most. I mean, you have to, well, if you want to do anything interesting, you very quickly hit Turing completeness. So the very first computer, so the built by Konrad Zuse, before the Second World War, this was it started in 28, I think, and then when was it again? Anyway, the Z1, 2, 3, those were not Turing complete, but could already compute a lot, and basically afterwards, anything is Turing complete. Now, we can ask the question, if I give you a data set, could be, well, a data set can be a binary string, right? Because for any data set, really no matter what, we can come up with a small program that can turn it into a binary string, right? It may not be the most efficient way to do it into a binary string, but it doesn't matter. That doesn't matter. So we can think of data as a binary string. And now we can ask the question, how much information is in this string? Otherwise put, how random is this string? And that is exactly what Andrei Kolmogorov was working on in the late 50s, early 60s. How can we decide, is something random, yes or no? A very fundamental question. And until then, basically not answered. You had very complicated definitions, but how can we do this? And he approached this through the lens of computability. And he had a fantastic idea. Namely, if a sequence is completely random, right, and it's a long sequence, right, it needs to be long enough, what is the shortest program for this sequence? What's the intuition? No? Print sequence, exactly. I mean, that's not much of a program, is it? Right? And so basically the Kolmogorov complexity of a sequence is the length of the shortest program that can print the sequence and hold. And if the sequence is random, the Kolmogorov complexity is just going to be the length of the sequence plus some small constant, right? Because whatever, let's say, amount of bits you need to actually write print, quote, this, end quote, and so on and so forth, right? Suppose that I now have another sequence. I'll get to you in a second. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, and so on and so forth, right? I mean, that's of equal length as the random sequence I just gave to you, right? What would you say is the Kolmogorov complexity of that sequence? What is your intuition? If the random sequence is just print sequence, now we have something that's just 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. What would be the shortest program? What would it look like? Then you.
It's 0 and 1.
Yeah. Exactly. 4, I until, well, however many times. So basically, it's those few bits, right? 4I to n, right? For 0 to n, right? I mean, that print 0, 1, that number of bits, which is almost nothing, right? And the only thing we need to encode is n. Because that's, if I give you a slightly longer, that's the actual information in the sequence is effectively n. All the rest is just essentially a constant, right? Or can be treated as a constant. That's pretty cool, right? That if there's no structure, we get very long, right? And if there's a lot of structure, we get very short programs and anything in between. Now, that is the notion of Kolmogorov complexity. And we're going to be using this throughout this course quite a few times. I'm not going to go into full details of how you do everything with this and what you can do, because I just taught a seminar last semester. Might do this again next semester. For now, we need to use Kolmogorov complexity for what it is. Yes? Yes.
You're not saying, oh, there's like.
No.
So
Distributions don't exist.
yeah, so you random street, it's very likely that there's.
Yes.
So it's probably not.
If the string is long enough, then it is. Because you're right, I mean, there might be patterns, right? Let's take pi, right? I mean, pi is well, what would be the common? So I give you a sequence of pi, right? I mean, that starting from 3.14, right? I mean, and then very, very long, right? I mean, that what is the Kolmogorov complexity of that string of pi? would you say? Of length n.
I mean, showing.
Why? Why n? Yeah, so but well, I want pi, right? I don't want n. I want you to print a string of length n that has n digits of pi. Yeah, so I think you're thinking too complicated. Let me just say what I mean. There exists a very short program to print digits of pi. Right? I mean, pi is very structured in that sense, right? It's very easy to compute the first, I don't know, God knows how many digits, right? So therewith, just like with the 0101 example, we have a very short program and the only input it needs is n. So in that sense, you're right? I mean, it's a very short program and we can print pi up to almost arbitrary length, right? I mean, that's no problem. Now, pi is funny in the sense that, at least it's said, that for any sequence of digits that you can come up with of any length, right? Somewhere in pi, right? If we just go far enough, right? I mean, that we will find that set of digits, right? Which could suggest like, hey, wait a second, this means that random sequences can also be printed very shortly. But that is not true. Because where in pi is your random sequence going to be? Well, it's probably going to be very, very far, right? Meaning that you need to specify, well, a very large n, and well, the larger n becomes, then at one moment, the size of n that you need to encode, that basically is the Kolmogorov complexity of the sequence you want to encode, right? That becomes larger than the length of the sequence if you would just print it verbatim. In other words, let me give another example. Yes, it is possible that in my random sequence, 111 happens a bit more than you would expect. I say a bit more, right? I mean, not like significantly, lot more, right? Because then it's not random anymore, right? But if it's just a bit more, then I can, of course, change my program that, okay, you know what? Here, and there, print 111, and the rest, well, okay, this is the scaffold, right? I could do that. The algorithmic structure to print 111 and to specify where to insert it costs bits. And that cost needs to be outweighed by, well, not printing it verbatim. The moment cost is lower than printing it verbatim, we call it effective structure. Effective structure is structure in the data where we can algorithmically describe it more compactly than by just saying print. And if the string is random and long enough, there is no effective structure. And now I still went much further in Kolmogorov complexity than I planned, but I'm still gonna let you ask a question. Kolmogorov complexity is a theoretical construct because it's based on Turing machines. Turing machines work on binary strings effectively, but anything can be translated into a binary sequence, right? Even if it's truly any data in your computer is discrete. You can trick yourself, say like, no, it's continuous valued. Really? If you think about it, then no, everything is discretized, right? It's discrete. It's discrete. I can very easily, just mean in neural network terms, I can use a one-hot encoding, right? So for if I have now, let's say, 10 values, right? I mean that's and for each of the digits, I can say, okay, this is a 3, right? So the third one is 1, and all the others are zeros, right? That could be my binary string. For the next one, 1, okay, the 1 is on, and the rest, and so on and so forth. I can easily do that, right? And there's a very simple program to take pi to turn it into this bit string. What would be the Kolmogorov complexity of that transformation? It's nothing, right? So it doesn't matter how you translate your non-binary sequence into a binary sequence, right? As long as you don't actively do this the most stupid way imaginable, right? I mean, by making it stochastic and whatnot, but if this is a deterministic process, it does not matter, conceptually, right? But, Anton.
Binary string S is the only parameter, right?
Yes.
So we don't have like something in the sense of, okay, given a random binary string of length or something.
No. So in a way, what is a little bit hidden is that we have this Turing machine U, right? So effectively, we're looking for this program, P star, that we give to U such that it then spits out S, right? So S is the input. But U is basically, you could have this as a subscript, right? It's the cohomograph complexity with respect to U. Now, you have results where basically it says, okay, it does not matter if your sequence is long enough, it does not matter which Turing machine you use, right? Because just like with your favorite programming language, what is your favorite programming language? I don't know that one. Mine is Python, right? I mean, that's if both languages are Turing complete, right? I can write a cross compiler from Python into, right? I mean, that's and you can do the same, right? You can do the same. You can write a cross compiler to Python, right? Now, how many bits does this take? Yeah, this takes some code, right? I mean, this is a constant. Now, as long as the sequence S is long enough, this constant is not going to do anything, right? I mean, that's and if it is, then it just asks for a slightly longer sequence. This means that you, the Turing machine, whether we use or Python or C++ or whatnot, it does not matter on paper. In practice, of course, this cross compiler is quite a big chunk, right? I mean, and S may not be that long. So of course, then it might be that the one language is a bit preferable to the other, but this is what we call an inductive bias. Good. There's one major problem with cohomograph complexity. As beautiful as the theoretical construct is, right? I'm going to continue and then I'm going to ask. Okay, sorry. Then, okay, well, that's it's still true. Okay, then go ahead. You could say that cohomograph complexity is the ultimate compressor. It's the ultimate compressor. Because cohomograph complexity considers every possible program P, right? Every possible compressor is a program, right? So every possible, not just zip, not just rar, not just this, not all of them, right? Including all of those that we've never even thought of yet. They're all there. And it picks the one that is the shortest. This is a very good comment because this, hi Sebastian, the idea here is that we essentially are going to be using the idea that learning is equivalent, is the same as compression. Compression is comprehension. The moment that you understand something, the idea, you grok it, right? It becomes simple. You can compress it. Until then, the world is completely random, right? The moment you see the patterns, right? So you thought it was random, but actually there is this 1-1-1 pattern all the time. You were right, right? Okay, well then all of a sudden we have a simpler way to describe the world. Now, if we would have given, let's say, our life's experience or the history of the universe as a whole, and we can compute this thing, then we can figure out what is the optimal program. Well, we're not in that luck, right? We have to learn on the fly. So we are never in possession of P star. But while we learn, we basically find ever and ever better P stars. Or we approximate P star better and better. Unless, well, we drink too much, do too much drugs, or refuse to learn, right? And that is also possible. Good. Now, as beautiful as this construct is, I'm just going to try it one more, this sentence. It is purely theoretical and it's useless in practice. Cohomograph complexity is not computable, sadly. If only it were. If only it were, right? Why is it not computable? Does anybody have an idea? Yeah, that is definitely, well, a nuisance. A nuisance. I mean, I have to correct you though. I mean, actually, I'm going to let you correct yourself. Are there infinitely many programs? Suppose that our binary string, right, S, has a length, no, 1,000,000, right? Or we can make it an arbitrary n, right? N. How many programs would we need to look at if we want to, well, find the shortest one for this string? And programs are also binary strings, right? In the end. Yes, exactly, yeah. So let's say that one has length n. Right? So let's forget about the constant because n is so long that we can forget about that. How many binary strings are there up to length n? effectively 2 to the power n again, right? I mean, which is again a very large number if n is very large, but is it infinite? No. So it's going to take us a lot of time, but we can do it. We can do it, right? I mean, that's if we use black hole computing, right? Basically, we implement something very badly, put it in the computer with some, I don't know, nuclear energy device. We throw it into a black hole, right? Where time dilation happens, so everything goes very quickly. Then it will find the right program, right? In that sense, we just need to get it out of the black hole, and that is, well, still study, right? I mean, that's a topic for the research. There's another problem that keeps us from doing this. Yes.
Can't decide whether the program holds.
Exactly. That is, in a way, well, not so much a more fundamental, it's an equally fundamental problem. Because suppose that we now have a string that is just 0, right? Or actually, no, that's a 0, 0, 0, 0, 0, right? I mean, that's a, and we now have a program that is just, let's say, 1 bit long. And it prints zeros, exactly n zeros, right? I mean, in our Turing machine, right? Whatever language this is, maybe it's, I don't know. And then at n, it stops printing, but it keeps running. Is this now, is the Kolmogorov complexity of our input sequence, is this now 1 or not? Because the moment we say like, yeah, it is, then it's going to print 1, right? Or print another 0, right? I mean, or it could halt. Now, the halting problem is undecidable. So this nasty little detail here means that, well, yeah, this is purely a theoretical construct. But still, it's very useful to think about learning and to get inspiration from and try to approximate it. How can we approximate Kolmogorov complexity? Can we? Yes, we can. MDL. Finally, this is where we were going at, right? I mean, I thought these slides were just going to take like 2 minutes. I mean, I have no idea if I can finish this lecture today. MDL stands for the minimum description length principle. And MDL is the computable close cousin of Kolmogorov complexity. It's the statistically well-founded approach to approximate it. What we do is, at first, a slight play of words. We're not going to look at programs, right? We're going to be looking at models. But a model is just a program. Don't worry, right? I mean, for now. And we are given a set of models, M. Okay, let's think of all programs. And now the best model, M, in this set of models, right, minimizes this thing over here. What do we have? The length of the model we chose, the length of the program, length of P star, right, plus the length of the data given M. Well, in Kolmogorov, we don't have this term because we always describe it exactly, right? You could tease it apart, right? I mean, but now, if we would do that, if M, curly M, would be all programs, we're exactly at Kolmogorov complexity, right? We call this ideal MDL, but ideal MDL is as unideal as Kolmogorov complexity is because it's equally uncomputable, right? And equally unwieldy too, because that is also still a real problem, because black hole computing doesn't work. Now, rather than looking at all programs, we could say, you know what, in curly M, we only consider all programs that halt. We could do that, right? Don't ask me beforehand if a program is going to halt. I can't decide it, but somehow curly M is now all programs that halt. And specifically, right, all programs that also can spit out the data. Well, that sounds a bit like a play of words. However, we have a name for this set curly M. You already gave it, set of compressors. Specifically, the set of lossless compressors. Every program that can spit out the data verbatim as it is, right? Not verbatim, but basically as it is, right? I mean, that's in using different patterns or not, right? I mean, there's different ways to make it more effective, the program, right? Have a short, well, out of those, we want the one that is shortest. So for the sequence where 1, 1, 1 is truly a pattern, well, that probably should be inside the model, right? Because if it's not in the model, well, if it's going to write 1, 1, 1 independently, it's going to waste essentially bits for having to say that here's a 1, here's another 1, here's another 1, rather than saying 1, 1, 1 in one go, right? Now, under that example, what does this mean? The one where we do have the 3, 1 pattern, that has a slightly more complicated model, because somehow it needs to have a code book of some kind where this pattern is encoded, but that gives it a benefit on this side, because it can describe the data a bit more easily. Think of the boxes, the colorful boxes that we had earlier, right? The moment that I were to have just all the individuals, right? So I really just have ones and zeros. Then the model is a bit simpler, but I spend way more bits here than I strictly have to. And this is now also the answer to your question earlier. When do we include something in the model versus in the data? When it's effective structure, when it happens often enough that we get a gain on describing it, the data with it, right? That is outweighed by the cost of needing that vocabulary term, right? To making the model more complicated. That is the general idea of MDL. Now, in practice, we will never use curly MS or lossless compressors because we don't even know which those are. But what we can do is we can define a model class, let's say, in our case, models that consist of patterns. What is then a model? Well, it's a set of patterns. So all sets of all possible patterns, right? So it's doubly exponential. It's a very large search space. But we can now ask the question, which set of patterns is best for the data? Well, the one that describes it best. It will only include patterns if it exploits effective structure, otherwise we don't want it. Hey, that is pretty neat, right? And this is exactly what we were developing next. So a model looks like this in our setup right now. Model, we call this a code table back in the day because, well, it's a table, 2 columns with item sets or patterns in the left-hand side. So this is that somebody bought products A and C, right? And this is B and D and so on and so forth. And on the right-hand side, you have the associated codes. How we get to those, right? How we pull it out of thin air, I'll explain in the following. But the idea is that we want to have a code table with few codes such that the codes we use as often as possible, namely then it lohnt sich, whatever, it's worth it to have them very short, right? That in total we need the fewest bits to describe our transaction database. That's what we're after. So this is for an example, running example with a database over 5 products, right? Because if I use my 10,000 product supermarket, it would not fit on the slide. How do we get to the codes, right? And that's the first step. Suppose that I now look at what you bought in my supermarket. You bought a B, C, and E, right? I mean, that's bread, chicken, and eggs. Or beer, chicken, and eggs, right? I mean, let's be the beer, right? It's beer, right? Yeah, so I think so. Good. What are we now going to do? We need to look at how can we describe, how can we explain that transaction, right? Those 3 products using the patterns we have. And what we do is by constructing a cover. Effectively, we go over our coding set. Right? It's not a code table yet because there's no codes, right? So I call it a coding set. And one by one, I check if the pattern we're looking at, is this present in the transaction we're looking at? For AC, this is not the case. So I move on. BD, is this part of BCE? No. So I move on. CE, yes, CE is present, right? I mean, that's, so I add CE to the cover of the transaction, right, of the row we're looking at. I add 1 to the usage count of that pattern because I'm using it once to describe something. And I remove C and E from the transaction. That last part is a design choice. We can relax this to a certain extent, but you want to avoid that the next pattern, here there is none, but that is going to explain CE again, right? And we want to have one pasta pattern. We don't want to have all of the variants, right? So in order to steer inductive biases, to steer towards one pasta pattern, we remove this from the transaction. It also helps to speed things up. Okay, we continue. Do we see an A? No. Do we see a B? Yes, we add the B, we remove the B, and so on and so forth. This is the cover of this one transaction. Now, if I were now to give you this coding set and this database, right, and I give you a minute or 2, you can do this for all these transactions, right? I mean, you would turn the database into essentially this cover and we would arrive at this set of counts, right? I hope everything is clear so far because there's no like rocket science or anything because this is data science. Now, we have these counts and we now need to turn them into codes. So we need to dip again into a bit of information theory. Information theory is essentially statistics. Statistics is, well, not effectively probability theory, but it's all very joined, very closely related. So we need the probability of a code. So it's a probability for AC. What is the probability for AC? Well, how we define it is that we have here the usage of 3 because we have it here 3 times, right? AC, AC, AC. out of how many codes, right? So if I would throw a random a dart randomly into these yellow boxes, assuming that all these boxes are equally sized, right? I mean, that's, well, then it's 3 over, what is it, 13, 10, 16, yeah? Okay, so anyway, 3 over whatever the number of, the total number is. That is effectively the probability of randomly grabbing a code for AC, right, out of the entire encoded database. As you write down like this. So the probability for X, given the cover and of the database, is the usage of X, how often did we use it, over the sum of usages. And now, taking a leave out of Claude Shannon's entropy paper, we know what the length is of the optimal code for such a probability. Namely, it's simply the negative logarithm to base 2. I'm so used to that I don't even write it anymore. Negative logarithm to base 2 of that probability. That's the number of bits, the fewest number of bits that we need to be able to uniquely identify that the message was X, right? Out of, well, whatever this distribution can spit out, right? In our case, the probability of AC out of all of those, right? And following the usage count that we've seen. That is the number of bits. You might arrive, if you say, like, if you think about this, hey, wait a second, unless these probabilities are all 1 over power of 2, I might arrive at a fractional number of bits. And that breaks my brain. Yeah, it breaks everybody's brain, right? But you don't have to worry about it. Because in the limit, right, if the data becomes long enough, large enough, right, effectively it becomes a rounding error for the code of that is least frequently used. Beautiful proofs for that, you just have to trust me, right? Fractional bits, don't imagine them, just use them, right? Also note that we are not interested in actual codes. I'm not interested in knowing how to write 1, 1, 0, and then, well, half a 0. I don't care. What I care about is that for AC, I need so and so many bits. And for CD, I need so many bits. That's the only thing I need. Note that this calculation here, on the one hand, it's optimal, it's optimal code length. However, we are ignoring currently a few things, such as how we cover the transaction. Namely, what I was doing here, oops, go back, here. I removed C and E from here. So automatically, had this one been, let's say in the middle here, would have been BC, well, I'm not using the knowledge that I'm not using BC if I've already used CE in computing the code lengths, and by not using information that is effectively available, my encoding is less efficient. I use more bits than strictly necessary, right? So this approach is suboptimal. We don't write it exactly in the paper, because nobody would, but be critical, right? Okay, now there's a good reason why we're not optimal, because the moment we do compute this optimally, then it's not just NP hard, right? And I'm not going to ask if people know what NP hard is, but it's even hard for a probabilistic Turing machine, which means that, well, this is pretty much one of the worst complexity classes you can be in, right? I mean, that this is called PP hard, which Nikolai, my co-author, found. He's a bit immature. He found this very, very funny. And I have to admit, I also think it's funny. Okay, good. So we can compute these code lengths, right? And we have shown how we can do this, but it's essentially not worth it. Good. Now, yes, sorry. Yes, exactly. Okay, good. Now, what is the encoded length of a database given a cover? Well, this is very simple to compute. It's namely for every pattern X, right? Every pattern X, how often do we, well, have to describe it, and what is the length of the code for it? Well, we already know how to compute this, and so basically we again go over the table, and then, well, whatever the code length for X was times how often we use it, that's it, right? And we just sum it. This means that we go from the left-hand side from the cover. 2 slides back, I showed you how to compute these code lengths, right? I mean, where effectively for CE, this is then the usage 2 over, well, 13 I have here. Whether this is correct or not, I mean, it should be the sum of these. I'm not going to quickly calculate this right now. That is the number of bits, and that's the width of that bar, right? I mean, I try to draw this proportionally. Now, if we now ignore these for a second, just to create a bit of space, I can now replace each of these cover elements, AC, with the corresponding code. Then I arrive at this, and it gives me exactly the code length for each of these transactions, which means that for the first row, the length of ACE given this coding set or code table, whatever you want to call it, is the length of the code for AC plus the length of the code for E, which is, in this case, 5.8 bits. Okay. I hope this is all reasonably clear, right? I mean, there's not so much to it. Before we're now really at MDL, we also need to encode the model, because what we've been doing so far was encoding the data given a model. But you somehow also need to know what are these codes. Otherwise, if I would send you the bits of the encoded database, you can't decode them. And the key idea, both in Kolmogorov complexity and MDL, is that the encoding needs to be lossless. Why it needs to be lossless, we can discuss later, right? But this is a very important point. Now, what is the model and how do we encode a model? There's many ways of doing such. We need to somehow transmit, if I have the model and you don't, I need to transmit the key information to you, such that you can reconstruct it. There's different ways on how to reconstruct, right? So I have to contemplate a little bit what is smart. We need to set up a protocol so that you know what bits that I sent you, what they mean. So one thing, how we can do this, is that suppose that you already know, aka I sent you a pigeon, right? And that what are the frequencies of the individual items? How often do we see A? How often do we see B, C, D, and so on and so forth, right? And that, well, I think that we can do this, right? I mean, now we can find a pigeon. Now, the moment you have these frequencies, you already have a code table. I mean, a very simple one where you only have these singleton patterns. You don't have like proper patterns, but you have a very simple one, right? You can compute code lengths for that one because you know how often A is used, how often B, and so on and so forth. This code table we call C0 or CT0. I mean, that's and we can use that code table to now encode the patterns that I want to send to you. So if I want to send AC to you, what I need to do, I need to tell you, okay, I'm going to send you a pattern of length 2. And then you wonder, hey, oh, what would be the first item? And I send you the code using this C0 of A. Like, oh, it was an A. That's so exciting, right? What's the second one going to be? I sent you a code for C or E or whatever the pattern is going to be that I want to reconstruct. And that way we can loop through each of the patterns, right? So for all of the patterns in the code table that I want to send you, which are being used, if they have a usage of 0, then there's no point in transmitting them, that are just redundant. The code length of X is basically using this independence model, right? That's also what it is. And then, well, but the code for that is what I sent you afterwards, right? So I sent you AC, and then it's okay. And this is the code word for AC. There's different ways of doing this. This is not optimal, but it works well in practice. And each and every time we try to tinker with this, maybe we win a bit here, but we lose a bit there. It's not really worth of optimizing further. Okay, good. Now we have a complete score. The total size of, why is the model now? Yeah, the model C. Okay, you could call this M. If I would write the slide right now, we would call it M, D. It's the length of the coding set, the length of the model, plus then the length of the data. We know how to compute all of those. Fantastic, right? Good. So now, magic trick. And now for the optimal model. I'm not a magician. And given that I'm not a magician and then black hole computing is also out of the window, this is easier said than done. Does anybody have an intuition about, well, how easy or hard is it to find this optimal model? Sure.
The completely optimal model, it would be just hard as finding Kolmogorov complexity. So
not necessarily. Not necessarily. Yeah. So of course, we're not looking at arbitrary programs. So it's not Kolmogorov complexity. We don't know exactly what is the expressiveness of these pattern-based models. So it's hard to say how hard it is truly. So it's even so far. What we do know, for example, so Sebastian Brandt was just peering into the room, and he works on theoretical computer science. Set cover is known to be NP hard. Set cover is effectively, if you translate it into our setup, I give you a set of patterns and you need to find the best cover of the data for the set of patterns. That is NP hard. Well, we're not really doing that because we already have this greedy cover strategy, right? So yes, if we wanted to do that part optimally, it would be NP hard, but we don't do it. So how is it? And there's many of these angles where basically the problem looks NP hard or worse. For example, this just computing these code lengths optimally, we already know this could be worse than NP hard, but what we're doing is simple. Basically, we don't know exactly how hard it is still, even after all those years. But we can reason about how difficult is it in practice. Because many problems are NP hard in theory, but actually in practice you can do quite well. How many pattern sets are there? If we just want to enumerate them in some order. So we already established there's 2 to the power I, where I is the number of items, number of patterns, right? -1, but I'll give you that one for free. How many pattern sets are there over these patterns? Suppose that I give you 10 patterns, right? How many sets of patterns are there? Anton? Exactly. So it's 2 to the power, 2 to the power I. It gets pretty scary, right? And mind you, we're now looking just at simple patterns, right? A, B, C, these types of patterns. Think about if we would have rules. AB increases the probability of seeing a CD. Then you have 2 patterns. And all of a sudden we have another layer of exponentiality. Or you translate one of them into a 3. Okay, that's the number of possible coding sets is enormous, doubly exponential. So, now, the worst part is, even if we don't know NP hardness or not, the score that we just presented, which I hope everybody agrees, like, hey, intuitively this makes sense. This whole learning by compression makes sense. Now, the nasty thing is that the score is not convex, so we can't just do convex optimization, right? It's not monotone. Adding a pattern to the model is not gonna, always improve the score, right? It's not like weakly monotone, or it's not submodular, right? It's also not so that the first pattern gives us a big gain and the second pattern gives us a slightly less gain, and law of diminishing returns, even that we can prove that it's not. Is it weakly submodular? Usually not. Which means that sometimes it is under certain circumstances which we can't really characterize. This is a very nasty problem. So, hence we resort to heuristics. We wrote this sentence in the first paper on this topic, and I wrote this sentence in every other paper I wrote on this topic. You could say I made this a pattern, just for the heck of it, right? I mean, I love the sentence. Hence we resort to heuristics. Heuristics are basically, we have no idea how to solve things optimally, right? Or we do, but it's way too slow. Let's do something greedy, something that makes sense. And the first algorithm that we introduced on this topic, the very first version didn't have this name yet, was in 2006. It got the name only in 2011, a more optimized version. It's called crimp. Does anybody know the word crimp? No. Okay, that means that there's very few people in the room who speak Dutch, or they are very shy, which Dutch people are not known to be shy. Krimp means to shrink. And the nice thing is, you can all pronounce it, right? I mean, perhaps you don't have the rolling R like I do, but that doesn't matter, right? I mean, crimp is also fine. What does crimp do? Crimp takes a database, like we've seen before, and it starts with an empty code table. Empty in the sense that all the singletons are present, the one that you got by the pigeon, right? I mean, that's a nice pigeon, we're not going to throw the stuff away. I'm going to quickly explain the algorithm, then I'll be with you. And we feed it a large pile of frequent patterns. We use one of the traditional algorithms to generate this heap of patterns, right? Way more than we would like to. Millions and millions of patterns, right? And we feed them one by one to the algorithm. Well, if we do this one by one, we need to do so in a particular order. In what order do we do this? Well, a smart order. Should we start with patterns that are very infrequent or very frequent? What would you say? And frequent in the database, right? We see them often in the database or not often in the database. What would you say? Yes, you, in the purple jacket. Yes, you. Why? I agree, but why? Yes, yes. Exactly, exactly. And if we use a pattern frequently, that translates into? Yeah. A pattern that it has a high frequency has indeed a high probability of being used often, like unless we have already its, well, let's say its close cousin right before that was even more frequent, right? So it can be blocked. But if we use it often, it gets a short code, which we use a lot, which means we can compress very well, right? So yes, we should use patterns that are frequent first, right? We should prefer those over the ones that are infrequent. And suppose that we now have two patterns that are equally frequent. I'm staying with you. I have one that is a very long pattern, right? High cardinality, right? Let's say the whole pasta pattern. And we have the bread and butter pattern. Which of the two would you prefer? They're equally frequent.
What first comes in mind is like we need breakfast and we can spend on that.
Okay, okay, then perhaps I asked it wrongly. So we have the pasta pattern, right? And I have another pattern. Forget about bread and butter, right? What I said about that. I don't know. Beer and diapers. Beer and diapers, right? I mean, they're equally frequent. Which of the two should we prefer first? Yeah, your neighbor?
Greater than.
Yeah.
Compress that first.
Why?
Because it has a larger length, right? So
Yeah.
we need to compress it so that we can understand that pattern quickly, rather than the pattern which has a smaller length.
Okay, yeah, I see where you're going. See where you're going. I'm going to take it from the other direction. The longer, oh, actually, perhaps, yeah. Sorry.
For the bigger one, because there is a less chance. That is a coincidence.
That is a very good intuition. Yes, indeed, indeed. So both your intuitions are spot on. I'm going to just be a bit more cutthroat, a bit more practical. If they're both equally frequent, right? Now let's assume that we don't have any pattern for those elements at all in the code table, right? Either for the beer and diapers or for all the pasta ingredients. With the longer pattern, I can essentially, with one code word, cover a large part of my data. I can save many of these individual code words, right, using those, with just one that I still use equally frequently. So I would first use the long pattern, and then afterwards, okay, then the shorter one is fine, right? So that's the general idea that we do this. So in that order, we go over these candidates, right? I mean, now there's also lexicographically, what is it? Yeah, this basically means if we need to break any tie, we prefer A over B, but there's no real idea behind it, right? This is how we go over this. Then we cover the data greedily. Now, in the example that I gave you, I already did so. Which patterns do we do first? We first use the longest patterns in the model, because they have the biggest chance of explaining as much as possible, right? Replacing many code words with one code word. So those we should use first. Because given that we don't allow overlap, if we would use them later, they might be blocked, right? That would be stupid. So cardinality first. Then frequency. The more frequent ones we want at the top, because exactly what you said, right? And then lexicographically. Okay, these are the heuristic choices that really drive this algorithm. What we then do, I need one or two more sentences. So if you that's unless you need to go to the toilet, if that's your question, then sure, go. So we have now an order over these candidates. One by one, I feed them to the algorithm. I add them to the code table. I cover my data. I compute my MDL score. And if it improves, yay, it stays. If it doesn't improve, if it gets worse, quite possible, I kick it out and never look at it again. And I go to the next one. And. This means that the complexity of this algorithm is the size of this pile times the number of records that we have here, right? If I just mean very crudely guesstimated. So in practice, it can blow up quite a bit, but there's lots of engineering tricks that you can do, because you can index things. And if I know that, well, the pattern includes an A, then I only need to look at records of the data that include an A, and so on and so forth. I am going to answer your question, but I'm first going to go to Anton because I promised him some attention.
Okay, so like these choices there, right? That we want to start with like the most frequent candidates, right? Do we have optimality guarantees for
No.
that, or is it just
No.
educated guessing?
Educated guesses. Educated guesses. That, really the intuition that we just had. That's really what it comes down to. I mean, optimality is really out of the window. But, I'm going to first go to her, because then it's you. Yes. Yeah, they're out of the window, out of the window. We pretend they never even existed. We never talk to them again. No, indeed. There is one additional trick that we add, which really makes the algorithm work, or work much better with than without this trick. The moment we accept a new pattern into the code table, right? Let's say we're now considered ABC, right? And we like ABC. ABC is great, right? And that we reconsider every other element in the code table that was already there and see if kicking it out makes things better. Because by the order that we do things, right? We go first for frequency. We might have in the first round, sorry, burps, we tried AB and we loved AB. AB was fantastic. But now we have ABC. And ABC in the cover, if the true pattern is ABC, we don't want AB anymore, right? So after every successful accept, we actually consider kicking out all the other ones one by one. Again, engineering tricks, we only have to reconsider kicking out things where the usage dropped and blah, blah. You can estimate things, right? There's all sorts of fancy statistics you can do there, still no optimality, but that is the general crimp algorithm. And this works remarkably well, I can say. Not to pat myself on the back, but we'll see that in action in a second. You have a question or a comment?
Yeah, because I also thought of like it's easy to construct examples where just optimality is broken.
Exactly.
You can see
Exactly. The moment you have these fixed orders, then no. That's just the cover. There you can already have like, well, it's effectively set cover is NP hard, right? I mean, so the moment that we use a greedy heuristic with or without overlap, yeah, we have an approximation guarantee if we do use the greedy algorithm from set cover, but that is, I think, a 2 approximation, which, well, in theoretical computer science land, this is fantastic. In practical land, this is the difference between something that is fantastic and something that's absolute rubbish. So, yeah. Guarantees only get you so far. Good. Look, this is how well crimp works. Is anybody impressed? Yes, exactly. It's the second line. You might not have seen the first time I showed this, or maybe you did, but like, okay, he's not talking about it, it's not important. It is important. This is the number of patterns that crimp reports for the same data. And all of a sudden, we are in the realm of, I don't think, 20 patterns or so, right? I mean, that it gets rid of all the redundant ones, and it doesn't include any spurious ones. Because spurious patterns are ineffective structure. They cost more than they gain. And redundant ones also cost more than they gain because we already have, let's say, ABC. We don't need AB anymore. Unless AB by itself, right, so without the C, is again so frequent that it can carry its own weight. Then we would include it. So, nice. Okay, that was 2006 to 2011. Then I moved after my PhD to Antwerp, and I started working with Koen Smets, my first PhD student. And we developed a new algorithm called SLIM. Who knows what SLIM means? I was just about to say, Anton, do you know Dutch? No, so you know what it means in English, I hope, right? That it also means something in Dutch, namely smart. So, smarter crimp. It's given away in the title, not evil or something. And as you can see, the picture of SLIM looks similar, but it's not the same. We got rid of the big pile of candidates. And that is very nice because we don't need to go over so insanely many candidates, right? We don't need to generate them first, right? Large-scale waste generation, because we're going to kick out most of them. We had the whole point, what you raised, okay, if crimp doesn't like a candidate, it never thinks about it again, right? Where sometimes you make choices that later you might regret, right? It happens, right? Such is life. Now, how does SLIM work? SLIM starts by using the singleton-only code table to encode the data. And then, rather than looking at the occurrences of patterns in the data, it starts to find patterns in how we encode the data. Because we realized when we started working on SLIM that compression is actually removing redundancy for a very large part, right? I mean, that's rewriting is also a thing, but it's redundancy. In our case, if we very often use the code word for A together in the same record as the code word for B, if this happens a lot, why don't we replace A and B with AB, with a new code word? And if we now see that the code word for AB is very often used together with the code word for C, well, why don't we combine AB with C? And so on and so forth, right? And maybe combining AB with C was a really bad idea. Let's not do it. So we still need to test these candidates. But the idea for SLIM was like, let's move from just looking in data space into cover space. So I don't have the slide immediately to pull up, but the slide where I had the yellow boxes, right, on the right-hand side. On that space, we're looking for patterns. So not on the left-hand side, right, of the data, or wherever it was, right, but really on the cover space. So not on the grays, but in the yellow ones. And those change every iteration. And the beauty of it is that we can immediately find patterns that have really a high chance of gaining us some bits, right? Redundant patterns are not even generated because why would we, right? I mean, there is no path to generate them. And if we now have removed a pattern, let's say, or yeah, let's say we've removed the pattern, but later on it turns out we need AB again. Well, if A and B, the code words are still used, then we will generate it again. That's the idea of SLIM. Well, and you get like a figure that looks like an 8, and who doesn't like an 8? This is both for one database. We can now move a little bit closer to the present day. Namely, we move from 2012 to 2015. Meanwhile, I was here. And we started thinking, well, doing this for a single database is nice. And I promise you I will show you some results, and hopefully you will like the results. But analyzing a single database is, well, only gets you so far. Suppose that I don't have just one supermarket, but I run a small chain of 3 supermarkets. I have a supermarket here in Saarbrücken. I have a supermarket in Homburg, right? So half an hour away, right, where the university clinic is. And I have a supermarket in Berlin, because why not, right? I mean, I like going to Berlin, so why not? Now, how would I now analyze this data? I can run SLIM on the databases for each individually, and I can find Saarbrücken patterns and Hamburg patterns and Berlin patterns. I could say, okay, well, I'm interested in the patterns overall, but yeah, are people from Berlin, well, let's say genetically they're going to be very similar to people from Saarland, but their buying patterns may differ a little bit. I may not have the same supply chains here and there, so not exactly the same products may be able to sell here. Many more people live in Berlin than here, so the patterns, the Berlin, let's say, I sell many more things here than in Berlin than in here. So can we somehow, in one go, figure out what is now similar and what is different between these individual sites? Can I automatically find, like, hey, wait a second, let's the first two be Saarbrücken and Homburg, right? There people love to buy Schwenker and Schwenker, right? I mean, that's and with some sauce to go with it, right? That's some mustard, right? I mean, in Berlin, people don't even know what Schwenker is, right? They will like currywurst with curry sauce, probably, right? I mean, that's so different patterns. But there are going to be some bread and butter patterns that, well, both people here and in Berlin buy, right? What we now would like to do is, or would like to get, is a set of these pattern sets, one for every combination of databases we find interesting. And then the patterns are going to be evaluated in the corresponding set. So the Schwenker pattern, actually, by the way, whom of you doesn't know what Schwenker is? Okay. Let's ask for the compliment. Whom of you is from Saarland? Okay, so then well, there's one person by definition knew what Schwenker. I guess everybody knows what a barbecue is, right? You know what a smoothing function is, right? If you apply a smoothing function to a barbecue, right, you have a Schwenker. What is that, right? I mean, you have the fire, right, or the coals or whatever, right? And then you have the grill thing, right? And normally it's fixed, but now we let it swing. And the Saarländisch German word for swing is to schwenk. Huh? And if you now put the meat or whatever you want to grill on the schwenker, right, then it gets grilled much more smoothly, much more evenly than if you just put it directly on the fire or right above, right? So it's a superior way of grilling. I say this as a non-Saarlander, right? I mean, it is. Now, that's called the schwenker, right? Now, what you put on top of the schwenker, typically some type of meat that is marinated, right, which is called schwenker. Now, this thing is not going to schwenk itself, right? So for that, what do you need? You need a schwenker. The person who schwenks the schwenker on the schwenker, right? That's basically the, so schwenkception, right? Nobody in Berlin knows what this is, but now you are all honorary Saarlanders, says the Dutchie. Good. Okay, anyway, the idea here is that if there are no common patterns between, let's say, Berlin and Saarbrücken, right? I mean, then the pattern set that is associated with exactly these two will be empty. The moment that there is a commonality, right? Let's say bread and butter, then it can either appear in the, well, Saarbrücken and Berlin one, but if this pattern is actually common also for Hamburg, then it should arrive in the, well, the pattern set associated with all three, right? And this way we can in one go compress all three databases in a smart way, such that we reveal what is different between the sites and what is common between the sites. And if you're not interested in supermarket data, I would wonder why, but we can think of, well, medical data again. We have three different classes of, let's say, well, patients, right? I mean, that this could be people that we know suffer from different variants of some cancer. It could also be, you know, we want to know, like, okay, wait a second, are there any differences between biological sexes? I mean, we're all human, but bodies work differently, right? This is very useful to see, okay, well, are there any patterns that we need to be aware of? This we can also do, well, for genetic data, but we can also do this in all sorts of different data. Being able to tell what is common and what is different is a really fundamental problem for which there are remarkably few tools. And pattern mining allows you to do this and also makes it visible what is then different, right? It's not just measuring that it's different, it's really telling you what is different or normal. Okay, let's go to some quantitative results, right? I mean, does it fly? I'm showing here the results of DiffNorm. I could have also pulled up the slide for Slim and Crimp, right? They all look somewhat similar-ish, subject to epsilon, right? But we have a number of relatively standard benchmark data sets. Benchmark in the sense that many people run their methods on it, not so much that we try to maximize accuracy, because this is an unsupervised task, right? The patterns that I find may be very different from the ones that you find. That doesn't mean that my patterns are better or yours are worse or vice versa, right? They're different. This is an unsupervised task, right? So it's not a benchmark. It's also not benchmarkable in the way that, well, other tasks are. We see these records, these data sets have, well, in the order of a few thousand records. Right, whoops, yeah, a few thousand records, right? Nothing to be too scared of, but still more records than you would like to look at yourself. The alphabet size I didn't plot, but this is like a few hundreds to thousands of items typically, not something like this. If we mine frequent item sets, and we do this up to a support threshold of 2, so basically every combination that appears at least twice in the data, right? If it occurs once, then it's not a pattern, right? Twice, it starts to become a pattern. We can discuss whether it should be 42 or not, right? But just these are the numbers, right? 58 million, 4.6 billion, and so on and so forth. I mean, outrageous. You don't want to look at those, right? Okay, let me not say what the second column, these are the closed frequent patterns. These are the ones which we can't expand without dropping the frequency. That's effectively what we do. So let's say that AB and ABC happen equally often, right? Let's report only ABC. That's the idea of closed. And if your data is very non-noisy, very deterministic, this helps to reduce massively. And you can see, right, we go from 4.6 billion to, well, more than 78 million, because then the miner crashes. But we're still in the realm of hundreds of thousands or millions of patterns. So this is why I say frequent pattern mining is useless. Then we come to our part, where I'm not saying it's useful, not yet, right? But at least the numbers are much more amenable. So we find code tables, pattern sets in the orders of typically hundreds for letter recognition, up to 1,400 patterns. Am I happy with these numbers? Yine. They are much lower than the first column, right? But I could also come up with a program of constant Kolmogorov complexity, namely return nothing, and I have even fewer, or just return the first one. So it's not size matters not, right? To quote the philosopher Yoda. But this column over here is what makes me happy. This is the percentage of bits that we need to encode the data with that number of patterns, with those patterns, compared to the number of bits that we needed without those patterns. Just the data that the information that the pigeon gave us. So lower is better here. And the key idea is that learning is compression. So the moment you go from 100% to 99.9, you've learned something. I don't know how low we can push this because I can't compute Kolmogorov complexity. But I do know that these numbers are pretty low, right? If we just need a quarter, or is it 14% of the number of bits, then we really found some core structure, right? Whether this is expressible in fewer patterns, that they're more easily interpretable, blah, 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 sure, I believe it immediately. But, well, that's work for future research, perhaps yours. Okay, numbers are great, but let's now also look at some qualitative results, right? I mean, that's what does it really look like? For this, I use a database where at least all of us should be able to interpret the results. The previous ones, I mean, who knows, right? Let me finish the sentence and I'll be with you. What I'm going to be doing here is show you some results from what we took from a conference that sort of straddles both data mining, so unsupervised machine learning, and real machine learning in the sense that supervised stuff, right? I mean, that's this is from 2008, so there's no deep learning type of things that we can expect here papers on, right? Just to calibrate your expectations. What we're going to do is we take the abstracts of this conference for over a number of years, and we turn this into a bag of words representation, right? So basically actually a set of words, because it's binary data, right? And every word just happens or it doesn't happen. I remove stop words and I stem, right? Just to have basically the grouping that you were suggesting for the veggies, right? This is why I do the stem. And what I then do, to show you also that this diff norm idea works, right? I split these abstracts into those that include the word mining, because I expect more data mining words there, right? And those that do not. And then what I then ask the algorithm to do is find me the patterns for mining, for non-mining, and that are common, right? The bread and butter pattern, so to speak. That's what I'm going to be asking. But first I'm going to be answering your question.
Because clearly 757 is not the 25.6% of 681K, or I don't know.
So these are the number of patterns, the number of entries in this code table, right? So the green one on the left-hand side. And this is the number of bits that we need to encode the data using these patterns compared to what we would need if we would have no patterns and only singletons, right? So basically compared to the stupid code table or the ignorant one, right? Because you can come up with many stupid code tables. Yeah? Yes.
Consider lossless compression?
Yes, only lossless. Because lossy doesn't make sense. I'll just leave it as food for thought. I mean, I'm already a few minutes over time, and I want to at least wrap up part of the story, so you're not gonna bait me into this. Okay, so these are the patterns, or some of the patterns, the top patterns. I order them by how much they ate compression for the data part on mining, right? I mean, what do we find? Association rule mining it doesn't have, right? Large databases, which that is the field that all the stuff that we're looking up, this pattern mining stems from. We see FP3. FP is frequent pattern, right? That's so how do you mine it? Pruning. Pruning is a very important part. We already saw how do we get rid of all these patterns? Frequent pattern discovery strategy. Okay, that makes a lot of sense, right? I mean, what's the last one? Support threshold. Well, you also now know what the support threshold is, right? So this really makes sense, right? Basically, this characterizes a lot of papers that were trying to mine all these stupid patterns. On the not mining part of the data, what do we get? Accuracy, learn, work. Why work is there, I don't know. But accuracy, I mean, learning, SVM machine, support vector machine, okay, right? That has nothing to do with mining, right? Clustering and partitioning, or training a classifier, or a learning approach. This makes a lot of sense, right? I mean, so I'm not saying these are the best patterns. I'm not saying it can compete with a transformer, right? But that's not the point here, right? I mean, the point is that do we grab out of this data combinations that are meaningful, that can give some insight? These ingredients of a hypothesis. I don't want to give the solution just yet, or I can't. These are the common patterns. I mean, every paper speaks about, solves a problem, presents an algorithm, and has experimental results. It's a framework or a general model. It's a method for large data sets, and so on and so forth, right? I mean, every paper does this. I mean, and every paper beats the state of the art, of course. That's so there we don't have a split. In other words, this works. It does find things that are specific and that are general, right? And mind you, text data is not ideal for what we're trying to do because it's very sparse, right? I mean, there is not so many of these patterns. There's many alternate phrasings that you can use, right? I mean, so it's really just to illustrate. So far, we've only looked at the transaction data. But from the beginning of the lecture, I already hinted at, we actually, as long as you can, well, actually no, there's many other applications where you can apply pattern mining. So the only thing we truly need is a notion of locality. Does a data record include a something? Or does part of the data include a something? We don't even need to have records, right? So for example, these formulas, right? These conjunctive formulas, we can relatively easily extend this to do that. For the molecules, well, the pattern language would not be ABC, it would be molecular constructs, for which, okay, fine, right? I mean, that we can easily do. And before you know it, we can do pattern mining just on molecules. And plenty of approaches have been proposed for different data types. And we'll see perhaps one or two later in the lecture, but not right now. I mean, later in the lecture series. I'm going to give you one example, though. This is a result that I personally liked very much. So Frauke Hinrichs wrote her bachelor thesis in my group a number of years back, and she extended this diff norm idea to sequences, right? So diff norm does not know anything about sequences, right? It was really just a set of words. And she extended it to sequence models. And what we have, she applied it here on the presidential addresses for different eras. US presidential addresses, right? I mean, the ones like Trump also then gave his rambling version. This was before the second inauguration. And what you basically split this into different eras. And what do you see? That, well, in the early years, right? So after the founding of the US, some of the patterns were like inland frontier and foreign nations. Yeah, it was still fighting the colonial oppressor. Then a bit later, I forgot the exact years, but civil service, social order, really like founding a nation and building it up, right? I mean that interstate commerce, race was of course, was still a very big theme in the US. You can really see the development of the US just based on which patterns we see in these speeches. What is important, what not. We also have some bread and butter patterns because, well, it's always my fellow citizens. This is how they typically start. Well, in the US, money is king, but the army is omnipresent, right? So Army, Navy, what is it? Men and women for Almighty God. Every speech, or not necessarily every, but many speeches include this. So if you would not know anything about the development of the United States, right, then I'm not saying this is the best tool to get the insight, but you get some insight. And this method, it can't even read, right? So that's pretty nice. So are these models any good? I'm going to flashcard. Because if you just look at numbers, yes, but like I said, you can already come up with a trivial algorithm that does better, right? They give something that looks nice, but is this now good? So the proof of the pudding is in the eating. We looked at many, many different applications. I'm going to quickly show you one. Classification. The idea, what we wanted to evaluate, is that if we have two classes that have different distributions, we should get different pattern sets from those classes, right? This was back in the crimp and slim days, before we had diff norm, right? I hadn't even thought of that. Now, what we can do is we can extract these two code tables, and you would expect that the code table for database 1 is better at encoding elements, entries from database 1 than code table 2. And code table 2 should be better for this, right? Because it's tuned for those distributions. If these two distributions are the same, well, they will do roughly the same, right? Then they can't. We can use this notion to do classification. Namely, we can look at if the encoded length of a transaction, given the code table we got from the one database, is smaller than the code length for the same transaction using the other one, then effectively, if you remove the probabilities of the logarithm and you rewrite it, we say that the probability of that sample being drawn from this distribution is higher. Well, that is a notion we can use very easily to classify. So what do we do? On the right-hand side, we split the database. Oops. Oh. No, away. We split the database into its n classes. We crimp or slim each of those. And then for an unseen transaction, we just assign the label of that code table that encodes it best, right? Not really like Nobel Prize worthy. Our goal was to show that, hey, yeah, we find different coding sets for different distributions. We were somewhat surprised, so we expected okay. We were somewhat surprised that what we get is a classifier that, at least back then, probably right now we can do better, but hey, this is some time ago, right? Was on par with the top most tuned classifiers. Yeah? So we're talking about SVM and kernel machines. If we would really tune them exactly for this data, out of the box without any hyperparameter tuning, would do equally well, which was, well, encouraging, you could say, right? We really pick up something that is useful. Now, we can do one step further, and this makes these patterns so useful. First of all, let me actually just show you. This is an example from the wine database, right? I mean, I love wine. It's the same transaction, but encoded using the code table for label 22, that's the class label, or label 9, the other class label. I think this is red and white wine, right? I mean, the blue bars are, again, just like previously, the number of bits for the codes, right? And they correspond to the green pillboxes. Those are the patterns corresponding to those codes, right? The same transaction. Which label do you think is the true label of transaction 1? In other words, which of these two code tables recognizes more or sort of likes this transaction more than the others? Exactly. Yeah, exactly. So indeed, so shorter codes, which mean like these combinations are much more prevalent for that class than for the other. You can also see that it uses many more patterns, or many, 1, 2, 3, 4 patterns, and then some chaff, right? Whereas here, it can use these two, and then the rest, this is weird, right? White wine doesn't behave like this. So just by, well, this is why the classifier works, but you can also look into it. You can also tell, for example, an even more extreme example, perhaps I should have done this the other way around, where the bottom one doesn't recognize anything, like what is this even? Is this wine? I don't, not where I'm from. And the other one does recognize it very well. Now we can also use this to now contemplate if we would flip, for example, for code table for this one, right? Maybe if we would flip 1 into a 5, right? So 1 is a particular value, right? Let's say the acidity is this, right? And 5 is maybe like a lower or higher acidity. If we were to flip it into that, then all of a sudden the compression could all of a sudden improve massively. And now we can consider how many flips do we need for that code table to be very happy with this transaction. That allows us to detect how robust this classifier is. It allows us to explain what is it really looking for or not, right? We can also do one other thing. And this is the result I'm perhaps most proud of in my perhaps career. It's perhaps the simplest idea. It was also with Koen, a year before Slim. We wanted to do anomaly detection or outlier detection, very similar. One of the key approaches is one class classification. So basically you have data for only one class, and then for an arbitrary sample, you need to say, is it from the class we've seen or is it from something else, right? All very related problems. These are very difficult problems. And many methods struggle enormously with this because what is normal? Well, what is normal? We know the answer. But we compress. Other methods struggle enormously if I give you a training database that includes a few anomalies, because it might include those in compression doesn't care. Compression is a complete honey badger in that regard. If I give you a database with a few anomalies and I ask you to compress it, is your compressor going to overfit on these anomalies? No, because they're going to cost more bits than they gain, right? We just print them verbatim. Effectively, what we did in this paper, we take a database, we run crimp, and we look for each of the records after we've compressed it, right? Or after we get the code table, how many bits do we need for this one transaction? effectively, how long are these blue bars, right? And suppose that we now would find this transaction in the database for code table 9. But if all the others are encoded much more compactly and there's this one string, that's the anomaly. And the same trick as I just described, let's flip a few things. And if like by flipping 1 into 5, we can make it completely normal, like, well, is it then truly an anomaly or is it a measurement error? Probably the latter, right? This way we can detect anomalies essentially without setting any parameters. There's a significant threshold you need to set for how many false positives are you willing to endure. Extremely high accuracy. Out of the box. Super versatile. We don't need to measure distances between records, which all other methods do rely on, implicitly or explicitly. And we can tell, like, why does it say that something is an anomaly? Now, why am I proud of this? This was inspired by a project that we ran with the University Hospital back in Antwerp. And they were interested in building a system that could predict if a newborn has a particular metabolism disorder called MCAD, MCAD disease or disorder. This is a rare disease. Rare diseases are diseases with a prevalence of less than 1 in 10,000. In this particular case, they collected data over all of Flanders for, I think, 20 years. And they had over all hospitals and whatnot, right? And they had a whopping 6 positive cases. This was all the positive data they had, right? Out of hundreds of thousands of, they take a heel prick blood sample and they analyze it, right? And that's, they give it to some doctor, which then raises the question, how do these doctors then do this? So yeah, this looks weird, right? That's basically how they do this, and then do all sorts of other tests. And the question was, can we automate this somewhat, right? Well, what we did is we ran our compressor on this heel prick blood sample database. And the doctors, they didn't tell us which records were now the true anomalies. We had to give them. And what we did know is that there were 6 real ones, 2 prototypes, where they asked the doctors, what would you say is a real MCAD case? And they drew something and like that. Now, our method identified 12 anomalies. We were a little bit sad because we wanted 6 or 8, not 12, right? I mean, that's... Then we gave them to these doctors, and they were over the moon. Because the 2 most anomalous things that we found were the 2 prototypes. Because no way if this would be actual babies, they would not be alive, right? That's just impossible, right? And that they were so exaggerated. Then were the 6 actual anomalies. And the other 4, where we also found, were actually patients, babies who suffered from another rare disease that these doctors did not know were even detectable by the features, by the heel prick blood sample that we found. Now, if that's not nice, and if that's not useful, then I don't know anymore, right? So this is, if I was not already in love with compression and patterns, that was the moment where it really became a very strong relationship. I'm going to wrap up because it's now on the hour. And the next few slides are nice, but I don't think they're strictly necessary. So if we need them at any moment, I will repeat them. I will show them in a later lecture. Otherwise, just take them as food for thought. Thank you very much for your attention.